Partho, would you start
Oh,
introducing, ma'am?
as you wish.
Yes, yes, sir.
Okay, madam. Very good evening to the participants of ATAL FDP on Quantum Age Intelligence 7th session. So the speaker for this session is Dr. Mahua. She is a very own associate professor of our department in MCKVIE. She completed her PhD in image processing, machine learning, medical imaging from Maulana Abul Kalam Azad University of Technology, West Bengal. She received Best Paper awards for several publications. Her current research interests include quantum machine learning, cloud computing, and Internet of Things with applications to different important fields. She has successfully completed a quantum machine learning based project sponsored by Government of India and AWS. She has published QML based papers in SCI journals. She served as session chair and invited speakers to many events. So I'd like to ask, request Dr. Pal to start the session. Very welcome, madam.
So I have shared my screen. Is the screen is visible?
Yes, madam.
Okay. Good evening, all the audiences present here. And thank you, Partha sir, for your kind introduction. What I mentioned that the topic of my lecture is quantum machine learning. Specifically, I would like to focus on quantum neural network in this lecture, as QNN is quantum neural network is as of now my domain of research interest. So with this introduction, I am formally starting my presentation. And what are the objectives that I would like to cover in my lecture is the objectives of today's discussion will be the architecture and components of quantum neural network, then the relationship among the different components, then quantum neural network optimization. After that, I'll be discussing hands-on session, how quantum neural network is optimized, and the most important session of this lecture is the application, some of the applications that we have developed during central government funded project execution. Those are the different applications. Some of the applications I will be discussing. So, first of all, we had to understand what is quantum neural network and how it is related to classical neural network, and what are the components of QNN, what is the analogy of the classical neural network and quantum neural network, and the technical understanding of the components, etc. After that, we'll go for the practical implementation of the neural network training or optimization. So, if we consider the real scenario nowadays, and if we consider the classical ML, then in the earlier era, what was the focus of the scientist was to find out the individual techniques for classical ML. But at the beginning era of the quantum ML, the focus of the scientists are how to borrow some techniques from the classical ML domain and to reuse that idea in the quantum ML domain. So that is the difference. That is the beginning era focus of beginning era focus of classical ML and quantum ML. And what is the current scenario? The current scenario is like that. The classical ML focus is on the size of the models So why am I telling size of the models? Because, for example, if we consider, say, for VGG16 model, we are considering a very famous model known to all, that is VGG16 model. So that is a convolutional neural network, well-established convolutional neural network model. Now, so there are many layers, say for example, convolutional layers, pooling layers, fully connected layers, etc. And the total learnable parameters in VGG16 is approximately 138 million. Number of trainable parameter is 138 million. That is the current scenario of classical ML. But what about the current scenario regarding the quantum ML? The scientists focus on capturing the hybrid architecture, utilization of hybrid architecture. What does it mean? Hybrid architecture means some part of the training, some part of the task, a full task is there, and some part of the task will be executed in the classical computers, and some part of the task will be executed in the quantum computer. That is to exploit the hybrid architecture, to extract the best out of them. That is the current scenario regarding quantum ML. So that is the difference between these two domains, quantum ML domain and the classical ML domain. So we are moving forward to the next slide, where we are discussing about motivations. My lecture topic is quantum machine learning. Particularly, I am focusing on quantum neural network. So what is the motivation? Means why are we actually interested upon it? So I am not discussing what superposition is, what entanglement is, because 2-3 days lectures already we have attended, and we have heard so many things regarding different inherent quantum properties, etc., fundamental quantum properties, etc. But by utilizing those fundamental quantum properties, that is superposition and entanglement, how we get benefited out of that while implementing quantum neural network, that is the motivation of my research interest. So by utilizing superposition, means a number of states that is present at one time, so we can exploit parallelism in computation. That is, we are heading towards less computational complexity, less time complexity. And entanglement, another inherent property of quantum, that actually helps us to capture the feature correlation very effectively. And what is the joint benefit? The joint benefit is that we can, with development of the quantum domain, one day may come when we can develop a model which is very powerful and which is able to extract very important features from very limited number of samples and utilizing very limited number of features. And as it is able to learn from very few parameters, very few learnable parameters, hence it is very much computationally efficient, and that is time complexity and computational complexity is very less. Also, as the number of parameters is very less, number of learnable parameter is very less. So it is also the space complexity is also very less. So that is the motivation, means that is the point of interest, why we are actually heading towards from classical neural network. Why are we actually heading towards quantum neural network nowadays? Why are we trying to develop the field? Now, in this slide, what we can see, this is the quantum computer, QPU, quantum processing unit. That is the quantum computer that is available in TCG Quest Kolkata. In one of my visit in the DCG Crest, I captured this photograph. This is a 1 qubit quantum machine, and it is used, it uses actually superconducting qubits. So in our Kolkata, at TCG Crest, this particular quantum computer is there in their lab. So now I'm formally entering in my topic. That is the first objective was that I discussed. The first objective was the architecture and the components of quantum neural network. As we can see over here in the slide that there are three different modules, 1, 2, and 3, three different modules. This particular module is data input module. This particular module is data process module, and this particular module is extract output module. So there are three main modules, and in between there is an optimizer, which actually optimizes the neural network, optimizes the quantum neural network, actually optimizes the parameters of this particular circuit. This is the input layer, this is the output layer, and in between there is a quantum circuit. And this particular optimizer actually optimizes the parameters of the circuit. How it optimizes, we will be discussing in detail. So before that, we are now got familiar about different modules of a quantum neural network. Now, within this circuit, these are the data encoding layers. Those are the RX gate. In the picture, we can see that the RX gate is applied at the input layer, and some RY gates are applied on the circuit parameters over here in the data process module. And some of the gates, entanglement gates, that is C0 gates, are applied over here. If it is Q0, Q1 and Q2, 3 qubit circuits. So Q0 and Q1 are entangled with each other with a C0 gate, and Q1 and Q2 are entangled with each other with another C0 gate. Further, Q2 is again entangled with the Q0 with another C0 gate. This way, the entanglement is actually implemented. What are the different types of entanglement that we will be discussing shortly? And after that, we have put three measurement units on the 3 qubits so that we can get the output. So up to with this knowledge, we are moving forward to the next slide. This slide is regarding the data encoding or data embedding. Whatever may be the data, say for example, it is a time series data. For example, it is an image data or a tabular data, whatever may be the data. The input layer actually embeds the data, the classical data. These are the classical data. And after data encoding, we get the quantum state actually. Now, we are trying to discuss about angle encoding of data. So, as we can see over here that we may apply, say for example, we are entering through this where we are entering the classical features. And on those classical features, we are applying Rx, Ry. We may apply Rx, Ry, Rz, etc. rotation gates. Here, Ry gates are highlighted because arbitrarily it can be said that the Ry gate is applied on the classical feature. So this is the analogy on the block sphere. So we all are familiar with block sphere, and Ry gate, it actually rotates the qubit on the block sphere. Block sphere is a sphere, means a football-like thing. So block sphere rotates that qubit or along the y-axis. Rotates the qubit along the y-axis that we can see over here. Here, the RZ gate tries to rotate the qubit on the Bloch sphere along the Z axis. It tries to rotate along the Z axis. Similarly, if we consider Rx gate, it actually rotates the qubit on the Bloch sphere along x-axis. This one is the x-axis, this one is the z-axis. It tries to rotate the qubit along the z-axis. So in this way, the angle encoding is actually takes place. This is the visual interpretation. Now, these are the visual interpretation, and what are the mathematics behind that? If we apply, say, Rx, here Rz and Ry gates, say these theta 1, theta 2, theta 3, etc. are classical features. Theta 1, theta 2, theta 2, etc. are arbitrary classical features. We are applying Rx gate, Rz gate, or Ry gate, and these are the actually the matrix. This is the matrix associated with Rx gate, means this is the mathematical operation Rx theta 2. If we apply Rx gate on the parameter theta 2, this particular matrix mathematical operation is actually executed. Similarly, if we apply the RZ operation, rotation operation along Z axis on some parameter, this particular mathematical operation takes place. Similarly, for Ry, if the parameter is theta 3, then cos theta 3 by 2 minus sin theta 3, that is on theta 3, this particular operation, mathematical operation is taking place. These are the standard Rx, Ry, Rz matrices. Now, regarding the entanglement. So, in first slide, we have seen that the middle module is actually after the input module, between the input module and output module, between input and output, there is the quantum circuit module. Now, different types of entanglement is possible. Say, for example, qubit 0, we are considering 3 qubits. Say, qubit 0 is entangled with qubit 1, and qubit 1 is entangled with qubit 2. So this is the type of entanglement. This type of entanglement is called linear entanglement. And if we consider circular entanglement, then the qubit 0 is entangled with qubit 1 and qubit 1 is entangled with qubit 2. Again, qubit 2 is entangled in the opposite direction with qubit 0. So this type of entanglement, this type of arrangement of C0 gate connections is called circular entanglement. And similarly, full entanglement, this is the circular connection, and full entanglement, all the qubits are connected with each other. So all the here we can see in full entanglement, all the qubits are connected with each other. So in an application specific way, we can use either linear entanglement or circular entanglement or full entanglement as per the applications required. Now, what we can see in this particular slide is that this is a quantum layer. Say, these are the Ry phi 1, Ry phi 2, Ry phi 3 are the quantum circuit rotations, means the feature representing Ry gates. These are not the encoding data encoding gates. These are the actually we are discussing the circuit module. We are now discussing the circuit module. So these are the feature extraction Ry gates. After that, we have applied in some fashion, we have applied the C0 gates, and the similar another unit of the circuit is here. This is the first unit, this is the second unit, and if we combine these two units, we can get this particular circuit. So that the circuit, in this particular circuit, there are actually two layers, the same first layer and second layer. these are connected with each other. So the question may be, why actually do we connect in this fashion? Connect the layers in this fashion. So this is actually related with the expressibility of the circuit. That is, the circuit, how much expressible my circuit is, that depends upon the layer, not only the layer, but also it depends on the application. That is, we have to add the layers in an application specific way. In some cases, multi-layer quantum circuits are more expressive than single layer quantum circuit. That is why I am discussing the layers of the circuit in this particular slide. Now, what happens at the input end? In the quantum neural network, what happens at the input end? In the input end, actually, the classical values are encoded so that we can get the quantum state. And what happens in the output end? At the output end, the quantum states are actually converted to classical values. Quantum states are converted. Once the quantum states are measured, the quantum states are actually collapsed and we get the classical output. Once it is measured, quantum state, once it is measured, we are getting the classical values. So, till now, we have discussed about the architecture of quantum neural network. Now, we are entering the next phase of discussion, that is how the quantum neural network is actually optimized. What happens in case of classical neural network? The prediction value, we are calculating the loss or error on the predicted prediction value by applying loss function or error function. And the classical optimizer optimizes the network so that the loss or error is minimized. This is the scenario for classical neural network. And what happens in case of quantum neural network? Actually, the classical values are pre-processed so that we can get quantum states. The after pre-processing, we are getting the quantum states. On that, the quantum neural network is actually working and it is giving some prediction. That is why prediction also we are getting from here also. Now, this is the point that we are applying loss function and we are using here the classical optimizer to optimize the parameters of the quantum circuit. And here is the point why it is called hybrid architecture. So, up to this, we have discussed the architecture. This architecture is given an architecture. This architecture is actually a hybrid architecture. Means the quantum circuit predicts something. After that, the loss function is applied. Then the classical optimizer actually optimizes the parameters of the quantum circuit. That is why this architecture is called a hybrid architecture. Okay, I am discussing some of the applications right now, and the applications, while I will be discussing some of the applications, I will be discussing the actual scenario, means what is the way, actual algorithm, what is the way, how we are actually how we actually optimize the quantum circuit. What is the algorithm, how the algorithms are actually implemented, that I will be discussing. So these applications, these works are funded by Ministry of Electronics and Information Technology, Government of India, and it is supported by Amazon Web Services for its bracket interface to execute the quantum computing programs. The principal investigator of this project is Professor Devashish De from Mahua, West Bengal. So this is one of the outcome of this project, that is the federated quantum neural network for privacy preserving early detection of diabetic retinopathy. This particular work has been published in 2024 and in Evolutionary Intelligence. For the time being, I am not discussing this work, and the next application is that is quantum learning based identification of retinopathy of prematurity. The DOI of this publication is also given over here. This is also the outcome of that particular project, this application we have developed. And this particular work has been published in August 2025. That is the system is the lightweight federated QNN system, that is QNN model based DR detection system. DR means diabetic retinopathy detection system. This is another system that we have developed, that is the privacy preserving federated quantum convolutional neural network for retinal image classification. This work also has got published in September 2025. So these are the some of the outcomes that we have obtained out of this project, and some of the outcomes also are there in the pipeline that will be actually we can get during a short period of time. So if we want to understand the architecture, because just now I have discussed regarding the QNN architecture. So these are the three, what we can see from this diagram, that this is the local, these are the three local centers. Local centers means local diagnostic center or medical service provider centers, etc., where raw data is available. Center 1, Center 2, and Center 3, where the quantum neural network is actually trained upon the raw data that is available at the medical diagnostic center or service provider. So quantum convolutional neural network we are actually using here in the local models. And these local models are hybrid, because these classical optimizer we are showing here three local models, and in these 1, 2, 3, these three local models, and these three local models are actually using classical optimizer. That is why the architecture is hybrid architecture. And we are actually not transferring the raw medical data, sensitive medical data to over the network. And only we are transferring this red arrow and green arrow, etc. These are actually indicating that data transfer arrows. These are actually data transfer arrows. That a red arrow indicates that the parameters learnable, only the learnable parameters of the local models are transferred to the cloud. And where all the local centers are sharing their trainable parameters to the cloud, where the federated aggregation takes place, and the green arrow indicates the transmission back of the aggregated QCNN model. That is, after federated aggregation takes place over there on the cloud, the federated model, that is the global model, is transferred back to the local medical centers, where this particular federated model is actually evaluated and tested with the raw data that is available. We are actually applying over here federated learning because raw data, we avoid the transfer of raw data over the network because that is vulnerable, because the medical data is quite sensitive. That is why. So for preserving the privacy of the raw medical data. So this is the architecture we have implemented. Only 3 local clients we have shown in the figure, but so many local clients may be there. Those are connected with the cloud. Now we'll be discussing the network optimization. Actually, in this architecture, these are the local clients where the network optimization takes place. So how that network optimization actually takes place, that we'll be discussing. In the cloud, no network optimization takes place, only the aggregation of the parameters takes place over there on the cloud. So network optimization. So what actually happens in case of classical neural network? If we follow gradient descent algorithm, two simple steps we actually follow. To compute the gradient, gradient means the first order derivative. The first order derivative of the loss with respect to weight we compute. And in the next step, what we do? Make a step in the direction opposite to the gradient. We are making the step, that is the two simple steps we follow. That is, first step is to compute the first order derivative, and the second step is, that is W nu equal to, that is weight nu equal to weight whole minus the eta, the learning parameter, multiplied by the derivative we have computed in the first step. These two simple steps we actually follow during classical neural network optimization if we implement gradient descent algorithm. Now, what happens in case of quantum neural network? We are actually supposed to implement quantum gradient descent algorithm. Now, how to actually compute the gradient of the quantum circuit? That is the problem. The problem is how actually to compute the gradient of the quantum circuit. So for that, we apply a famous rule. That rule is parameter shift rule. And we evaluate the PQC, that is parameterized quantum circuit. The quantum circuit is parameterized because we have seen theta 1, theta 2, theta 3, etc. parameters are there inside the quantum circuit. And during the optimization phase, we try to optimize the value of those parameters. That is why in quantum neural network, the quantum circuit is called parameterized quantum circuit, or again it is called VQC or variational quantum circuit, because during optimization phase, we try to optimize the value of the parameters. That is, the parameter values are variable. That is why it is called variational quantum circuit, that is, or VQC. So we try to evaluate the parameterized quantum circuit with the parameters shifted in both directions. So what is actually but this is the, at the bottom of the slide, I have given the reference. From this particular reference, we have implemented the parameter shift rule. This is the famous paper, General Parameter Shift Rule for computing quantum gradients. We have followed this particular paper. Now, just for two slides, I will be discussing some of the mathematical expressions just for the two slides. After that, we'll be shifting towards the implementation of parameter shift rule. So just bear me for two slides for some mathematical expressions. So theta is the parameter. What we can say from here, that theta is the parameter and O is the arbitrary observable. So O theta is the expectation of the arbitrary observable O. O theta is and we are trying to find out the derivative of O theta. This is the derivative of O theta. So as we can see from this particular equation, that theta is shifted forward by pi by 2 and theta is shifted backward by pi by 2, and the difference between these two we are calculating, and the difference is actually the derivative. What we can see from this particular expression. Now, Pauli-Gate applies rotation to the qubit about an axis in the Hilbert space. Hilbert space means the high dimensional space in the Bloch sphere. Pauli-Gate applies rotation in the Hilbert space. Thus, we can say that the expectation value is the function of the Pauli-Gate parameter and can be expressed as the sine function. Can be expressed as the sine function, where alpha is the amplitude. In the sine function, alpha is the amplitude. We know that alpha is the amplitude. And beta is the phase. Here we can see the phase shift of pi by 2, plus pi by 2 and minus pi by 2. So beta represents the phase shift and gamma is the displacement. I am discussing the thing in a lucid way. I'm trying to discuss in a lucid way the parameter shift rule. After that, after this slide, we'll be shifting towards the implementation of parameter shift rule. Now, what we have seen in the previous slide, that the parameter is theta, O is the arbitrary observable, and we are trying to find out the derivative. And this is the expression for computing the derivative. And what we can what we have discussed in the previous slide, that expectation can be expressed as the sine expression, that is alpha sine theta plus beta plus gamma. Gamma is the displacement. And if we apply a phase shift of pi by 2, then O theta will be O theta plus pi by 2. And the expression will be alpha cos theta plus beta plus gamma cos. It has been converted to cos because a phase shift of pi by 2 converts the equation, the sine equation, to cos equation. Similarly, if we shift in the opposite direction, that is we are taking minus pi by 2 is the phase, then we'll be getting minus alpha cos theta plus beta plus gamma. Only the phase shifting are taking place in two opposite direction. Otherwise, these are two similar equations. And if we subtract this equation from this equation, that is observable theta plus pi by 2 minus observable theta minus pi by 2, we are getting 2 alpha cos theta plus beta. So, by applying parameter shifting rule, here we are shifting the parameter theta in the positive direction, in the opposite direction. So we are applying the parameter shift rule. In this way, we are getting, by shifting the parameters, we are getting the difference between these two observables. And what we can see on the other hand is that the expectation is expressed as the sine expression, and if we simply find out the first order derivative of this O theta, then alpha sine theta plus beta plus gamma, simple derivative, it gives alpha cos theta plus beta. And what is the analogy? Simple derivative we are finding out, that is the finite difference law. This one, thus what is the analogy between these two expressions? Only a 2 in front of this expression. These two are same expression. So, for finding out the derivative, actually, this one is the derivative. For finding out the derivative by applying this parameter shift rule, we only require a factor of 1 by 2 in the front of this equation to nullify 2. This is the finite difference method of gradient optimization. So I'm telling the gist of my discussion. That is, we are trying to apply the gist of my discussion regarding optimization is that number 1 point, we are trying to apply quantum gradient descent. And we are borrowing in the first slide I have discussed, we are borrowing the idea, we are borrowing the techniques from the classical domain. So gradient descent idea we are borrowing from the classical domain. And by applying parameter shift rule, just we are finding out the first order derivative. This particular first order derivative will be multiplied with the learning rate and will be obtaining the new weight by applying the same equation I have earlier mentioned, that is weight new equal to weight old minus the learning rate multiplied with the first order derivative. So this is the all the things that is extracted from this particular slide. So now this is an elaborate view of the system that we have developed. I'll be showing you the implementation as well. So this is the elaborate system view where from different edge devices, these are the different edge devices, that is the tablet, the mobile phone, the laptops, etc. From where the images, medical images are available, from which the patches are extracted. Here we have not, for this particular system, we have not implemented angle encoding, but we have implemented another encoding type, that is amplitude encoding. After that, we have implemented one lightweight parameterized quantum circuit. This is the measurement unit. After that, the classical optimization we have executed to optimize the parameterized quantum circuit. Similarly, this is another client from where in the same way, after optimization, classical optimization of parameterized quantum circuits, the local parameters are actually aggregated in the cloud. And the model is returned back to the local service center. This particular federated model or aggregated model, this particular model is experienced with diverse types of image inputs. So this one is one hospital, for example, and this one is client number 2, that is another hospital. So this particular hospital, say this particular hospital is situated in North America, this particular hospital is situated in India. So some of the different types of medical images are collected from the patients over here, and some of the different types of medical images are collected from the patients in the North America. So diverse input images are obtained, and the parameterized quantum circuit is actually experiencing diverse input images, diverse samples. And in this way, when the federated model or the global model is formed, this particular global model is experienced with diverse input samples, and this particular model is very robust. Also, this is one of the advantage of creating federated model, and another advantage is that to preserve the privacy of raw patient data. So these are the algorithms we have implemented, and that is local for local training here. For local training here, this particular algorithm is executed, and in the for creating the global model, that is this particular algorithm is actually executed. Now these are the different results. That is, if I have 3 clients, that is client 1, client 2, and client 3. 3 clients are there. These are the validation accuracy, percentage, precision, recall, F1 score, and specificity before applying federated learning and after applying federated learning. That is, this particular results after FL, these after FL columns, this after FL columns actually indicate the global models, and these global models are actually robust, and these are client 1, client 2, client 3. These are the different local models. These are the all the evaluation metric values for the local model and the global models. So these are the different graphs, different optimization, classical optimization algorithms we have implemented, and we have compared different classical optimization algorithm with these are non-FL accuracy, means the local accuracy, local model accuracy. This is the epoch versus FL accuracy, federated learning accuracy. And these are the epoch versus non-FL accuracy, that is train accuracy, and green line indicates the validation accuracy. Similarly, this is the train accuracy, validation accuracy for FL. This is non-FL. The first row is regarding local model. This is that is the non-FL version of the model, and the second row is the federated version of the model. And this particular graph indicates the non-FL, the comparison between non-FL quantum model, non-FL classical model. Red line is for federated quantum model, and black line is for federated classical model. And this is for accuracy, and this is the same comparison of non-FL quantum, non-FL classical, FL quantum, and FL classical, the loss. Now, one question should come from this slide, that why are the graphs are not uniform? That is the irregular nature of the curves. Why the nature of the curve is so irregular? That is the question that comes from this slide. Now, there are several points why in quantum neural network the curves are so irregular in nature. The reasons are, I have pointed out here in this particular slide. That is the inherent probabilistic randomness of the quantum system is responsible for that. And the high dimensional quantum space causes the optimizer switch the directions frequently. And the small change in the angle, we have seen previously the block sphere, the angles are actually how the angles are changing within the block sphere. The small change in the angle contributes to a large change in the evaluation matrix. And quantum noise is, and another point, these are the three related points and related to the inherent quantum properties. But the fourth point is not related to the quantum properties, but related to quantum noise. Quantum noise is also responsible for the irregular nature of the curves. So first 3 points are why we are getting actually this zigzag curve. And the fourth point, the quantum noise, is also another culprit. And with the development of quantum hardware, we can overcome quantum noise gradually. We hope so. So the model that we have developed, that is federated quantum convolutional neural network. This particular model that we have developed, we have compared this particular system with some of the deep learning applications, available deep learning applications, and some of the quantum learning applications. We have compared with some recent deep learning applications, Wang et al. That is from 2020, another application from 2021. Because our application is involved with retinal image, the medical image we have used, that is the retinal image application. A similar retinal image application we have taken from the literature. Those applications use deep learning, classical deep learning models. This Wang et al. They have obtained the evaluation accuracy of 92.95%. And this particular reference, they have obtained the with retinal image. they have obtained the accuracy with deep learning models. They have obtained the similar work, but in the classical domain, they have obtained the accuracy of 89%. But our federated quantum convolutional neural network, our network has obtained the accuracy on the retinal image 96.8%. Similarly, we have compared with some quantum learning applications, some related quantum learning applications, because we have seen much of the applications in quantum learning domain. They have used different medical images. For example, this particular Sengupta et al., this particular work, they have used CT scan images. Some application they have used chest X-ray images. One example, only one reference we have obtained in the literature, that is from 2021, that used retinal fundus images, just like ours one. And the evaluation accuracy, Sengupta et al. With CT scan images, they have obtained 96.9%. With chest X-ray images, they have obtained in 2022, that is 98.1. And retinal fundus images in 2021, the only one paper in the retinal domain we have obtained, that obtained 80% accuracy. Our federated quantum convolutional neural network, this particular system, that have obtained 96.8% accuracy. And some of the evaluation results with that we have some of the evaluation results we have obtained while we have applied noise, that if we apply, say for example, we may apply the simulator for executing the system. We may use the quantum hardware also for executing the system. So here we have used default.mix simulator and default.qubit simulator. So what we can see from this particular table, that after applying amplitude damping noise of 5%, the damping factor is 0.05. That is, after applying 5% amplitude damping with 52 number of epochs, we are getting 70.58% accuracy. But without quantum noise, we are getting 97.06% accuracy. Simply, if we apply the phase damping noise, again, that is 5% phase damping noise, the damping factor is 0.05, we are getting actually the evaluation accuracy of 91.18%. Means without noise, the actual accuracy is 97%. But while we are applying 5% amplitude damping, this particular accuracy has drastically dropped from 97% to 70%. Similarly, while we are applying phase damping noise, it is also degraded from 97 to 91%. So what we can see, that is in the actual quantum computer, when we are executing the system, it actually faces different types of noises. So we have executed this particular system in United States, North Virginia zone, QPU also. The name of the QPU is IonQ Area 1. When we have executed this particular system in this particular QPU that is situated in this particular zone, with it gives the similar evaluation accuracy, that is 73.53% accuracy. And this drop of accuracy is actually for the quantum noise in the real quantum hardware. This is the evaluation in the NISQ hardware devices, that is noisy intermediate scale quantum hardware devices. That is the comparison. We can see that how much quantum noise actually, how much affects the evaluation result. So now I am moving towards the implementation of parameter shift rule. I have already discussed the mathematics behind the parameter shift rule, and the famous paper also I have mentioned from where I have we got inspired to implement parameter shift rule, etc. So So I think my screen is visible. Hello.
Yes, madam.
Okay. I'm sharing the Colab platform and this particular IPyNB I have shared, that is qgradient.IPyNB. We are going to implement actually the quantum gradient descent algorithm. And for that, we are installing three requiremements. That is three requirements we are installing: matplotlib, Qiskit. We are going to implement the whole thing using Qiskit. And for matplotlib PyLatex CNC for drawing the PyLatex is actually for drawing the circuit. For better visualization is actually for better visualization. So as it was runtime disconnected, that is why I'm installing it again. Qiskit we are installing, pip install Qiskit. And matplotlib, so PyLatex we are installing for drawing. Now we are importing some of the important requirements. Just like we are from Qiskit, we are importing quantum circuit to create a quantum circuit. This particular quantum, we need to create the quantum circuit object. That is why. And state vector is the simulator. We'll be executing state vector simulator. And Pauli is the operator that will be required for the measurement. So these three requirements we are actually importing. Quantum circuit object. This quantum circuit object is required to create the quantum circuit. State vector is the simulator that we'll be using, and Pauli is the measurement operator. Now try to recollect that there are three layers of a quantum neural network. One is input layer, after that the parameterized quantum circuit layer, after that the output layer. So here QC object is created with the quantum circuit. QC is the object of type quantum circuit and it has been created with 1 qubit. So we are creating an 1 qubit circuit, and on that QC object with 1 qubit, we are applying Rx rotational gate. And after that, we are applying the state vector simulator, and the observable is Pauli Z operator. Observable is the Pauli Z operator. So these are the functions. We are just executing the functions. Only 1 qubit circuit we have created. On that 1 qubit circuit, we have applied only one Rx gate, and the state vector simulator is required for simulating, for executing, and the Pauli Z operator is the output operator, measurement operator. So we are moving to the next code cell, where actually what is my objective for this particular section? My objective is to show how parameter shift rule is implemented for a circuit, simplest circuit with 1 qubit. For a simplest circuit with 1 qubit and one Rx gate is applied over there, means only one trainable parameter is there, that is theta. Theta is the only one trainable parameter. So on that only one trainable parameter, how that particular parameter theta will be optimized using parameter will be changed using by using parameter shift rule. Now, parameter shift rule I have discussed in detail. Forward means theta plus in the positive direction phase shift, and theta is our parameter. In the negative direction means in the opposite direction, the phase shift in the opposite direction, and we have multiplied with half, as we have seen in the here we can see, if we multiply with half, then this particular 2 will be cancelled out. So we are multiplying with 0.5 and forward minus backward. This is the raw implementation of parameter shift rule. So we are executing this particular code cell. Now, how to test? Before that, we have taken theta, but we have not taken any value for theta. Now we are considering an arbitrary value 0.5 for theta. So theta will be calculated by taking the value 0.5. Now, if we run this particular code cell, it is finding out the expectation value of theta. This is the expectation value. We are applying only one Rx gate. After that, we are applying the state vector simulator and we are measuring the using Pauli Z operator. And after applying parameter shift rule, the parameter shift gradient, this particular name of this particular function, this particular function return this value 0.5 into forward minus backward. That is the changed value. That value it will be printed, and the analytical gradient, that is the sign value. Sign means that that is the sign value means the first order derivative. If the first order derivative, we can take the first order derivative minus np sin theta, that also gives the same value. So by applying parameter shift rule, we can get the gradient in the same way. What we can see from here. So we have actually, by applying parameter shift rule, we have just modified, we have just calculated the gradient of only one parameter, first order derivative of only one parameter. Now we are trying to extend this particular task to build multi-parameter QNN. That is, the number of parameter in the parameterized quantum circuit is more than 1. With 2 qubits, this time we are considering, instead of 1 qubit previously, this time we are considering 2 qubits, and show how to train it using the parameter shift rule with Qiskit. Similarly, the quantum circuit object, etc., state vector, Pauli, etc., we are importing. These are the required packages. And this time, the QC object is created with 2 qubits. Now, the first qubit, on the first qubit, we are applying Rx gate, rotation X gate. And with the second qubit, we are applying RY gate. Arbitrarily, we are creating the circuit. First, on the first qubit, we are applying the Rx gate. On the second qubit, we are applying the RY gate. Then between 2 qubits, we are applying the C0 gate. Between qubit 0 and qubit 1, we are applying C0 gate for entanglement. Then we are applying rotation Z gate on parameters 2 and 1 both. On parameter, sorry. We are applying the rotation Z on qubit 1, and the parameter value is in the array. The name of the array is params. name of the array is, when we'll be executing this particular function, we will initialize, as previously we have initialized the value of theta equal to 0.5. Similarly, we'll be initialize some of the values in the params array. And state vector simulator we have used, then the expectation value is calculated over here. Previously, we have used Pauli Z operator because 1 qubit was there. Here we are applying Pauli Z operator, means the Pauli Z operator is applied over both the qubits, qubit 1 and qubit 2. Both the qubits on Pauli Z operator is applied to get the measurement. That is why Pauli Z. Now, how this parameter shift gradient can be computed for multiple parameters, because we have one array. The name of the array is params. This particular array is initialized with 0, first of all. Now, this particular array is filled with some of the values. We'll be providing the values during execution. What happens actually, these particular values previously we have computed phase shift in the positive direction and phase shift in the negative direction of only one parameter. Here, what we are doing within this for loop, we are actually shifting the phase of all the elements of the params array to the positive direction and to the negative direction. And in this way, forward and backward, these two values are computed for all the values of the params array. Now, after multiplying with half, the gradient values actually are stored inside the grads array. So, the grads array actually contains all the first order derivatives, contains actually first order derivatives of all the parameters. So this is the definition. Now, what we are considering, that initial parameters are 0.1, 0.2 and 0.3. What we can see from here, that we are considering the initial parameters are 0.1, 0.2. Arbitrarily, we have taken these values, and 0.3. And learning rate also we have taken arbitrarily, that is 0.1. Now, for the iteration in the range 10, that is how many iterations are taking place? The 10 iterations are taking place. Now, within these 10 iterations, what actually we are doing? We are actually executing the classical gradient descent formula, because by applying parameter shift rule, the grads array we have obtained. Inside the grads array, there are first order derivatives of all the parameters. Now we are applying the classical gradient descent formula, which is, as I have already discussed, that is new weight equal to old weight minus the learning rate multiplied by the first order derivative. That is, the params will be equal to minus equal to learning rate multiplied by the grads array. So in this way, we are getting all the new weights. So if we print all the values, we are getting this particular output. Means for iteration 0, the cost, means the error has been calculated, the loss has been calculated, that is 0.9759. And the parameters was initialized with 0.1, 0.2 and 0.3 initialized. After first iteration, the parameters are 0.1, 0.21986693 and 0.3. So what we can see from this first iteration, that the parameter 2 is the most important for this particular case. The parameter 2 is the most important deciding factor for this particular task. That is why the value of parameter 2 is actually changing in the epochs. In the next epoch, what happens actually, the loss or error has been computed. The loss and error previously was 9759.9759. Then in the next iteration, it has decreased and now the loss is 0.9709. And the parameter values, by following the gradient descent formula, we are getting the new parameter values for W1, W2 and W3. We are getting these three values, and the second, that is the W2, has been upgraded from 2198 to 2416. So in this way, all the 10 iterations are taking place. So what we can see from this particular implementation there, how actually the parameter shift rules, the first application we have implemented to compute the gradient using parameter shift rule. The second task is for how to use that parameter shift rule to compute the gradient and how the weights are updated where multiple weights are there in the parameterized quantum circuit. So with this, we have seen how the weights are actually getting updated. Now, I'm showing another implementation, that is how the binary classification takes place while QNN is trained using parameter shift rule. That is the quantum gradient descent algorithm, application of quantum gradient descent algorithm. Again, we have taken one toy example, and these are some of the packages we are importing over here. And as I have already explained, now we are building the quantum circuit. Here we are building actually within the comment line. I have written that here we are building the 2-qubit quantum neural network circuit, and QC is the quantum circuit object, and we are applying RX gate, and we are applying RX gate to this is the encoding layer, means say the X is the X actually is the feature vector. X actually is the feature vector. There are two elements, means two features are there, X0 and X1. We are applying Rx rotation on X0 and putting that value into the qubit 0. And we are applying the classical feature value Rx gate on the classical feature value X1. And we are putting that value into the qubit 1, the quantum weight which are associated with qubit 1. Now, the next part is the parameterized quantum circuit part, where we are applying the trainable rotation, that is the RY rotation. These are the weights 0 and weights 1. These are actually the parameters within the circuit which will get changed, which will get optimized during the training. And this is the qubit 0, this is the qubit 1. Means in both the qubits, the RY gates are applied. Now one entangling layer is there between qubit 0, because there are two qubits. Between qubit 0 and qubit 1, we are applying one CX gate. The control qubit is 0 and the target qubit is 1. And the final trainable rotation, we are applying one rotation Z on the qubit on the qubit 1, that is the weights equal to 2. So we are getting how many weights we are getting in this parameterized quantum circuit. We are getting actually 3 weights, 2 RY trainable rotation and 1 RZ trainable rotation. So we are getting 3 weights. These 3 weights will be adjusted during the epochs. And QC dot measure all, it actually measures all the qubits. Now, we are executing this particular question. And in the same way, this particular expectation function I have discussed in the earlier 2 tasks. I have only one thing is different over here, that is here we are applying the IZ operator. What I have written over here is this one, Pauli IZ. In the first task, we have used Pauli Z. In the second task, we have used Pauli Z. Z, both the qubits were applied with Pauli Z. And here we are applying Pauli IZ, means the first qubit is unaffected with identity operator. First qubit is unaffected and the second qubit is applied with the Pauli Z. That is why we are applying. This one is arbitrary implementation. So we are applying Pauli IZ. Now, what we need to understand, the new thing over here is the predict probability. How the probabilities are actually, E is the expectation value, and we are returning over here E plus 1.0 divided by 2.0. Means the example I have written over here, we are applying this particular expression we are applying. So if expectation is equal to -1, then P will be equal to 0. That is, the probability ranges between 0 to 1. We are fixing because we are handling the classification problem, the expectation values are mapped to the probability range. The expectation range is between, in quantum, the expectation range is between -1 to +1. So that -1 to +1 range, we are just mapping to the probability range that is from 0 to 1. This is only the mapping function. Now this is the loss function, because we want to compute the error or loss also. After that, the parameter shift rule. The parameter shift rule also I have explained, and the parameter shift rule actually here we are applying in the array, because all the three parameters will be updated. In the previous task, I have explained how parameter shift rule is applied for the array. So for the time being, I am backward and forward shifted expectations are calculated. For the time being, I am not explaining it again. And lastly, we require some visualization. That is why this particular draw QNN circuit will be required. This is a simple method or simple function which actually draws the QNN. And the training demo. Now, in the training demo, we have taken some arbitrary toy examples. 1, 2, 3, and 4. 4 samples we have taken, and the featured values are 0.1, 0.2, 0.2, 0.1, 2.8, 3.0, 3.1, 2.9. These are arbitrary values we have taken. 4 samples. And the class values. X is the feature values. X indicates the feature values. Y is the class value. The first 2 sample belongs to class 0 and the second 2 samples belong to class 1. And the array, the weights are arbitrarily initialized to 0.1, 0.2, just like the previous example. We have initialized with 0.1, 0.2, and 0.3. The learning rate also arbitrarily we have taken 0.3. Epochs we have taken 30 also arbitrarily. And this is the draw QNN function. We have previously defined this function. Draw QNN will help us to see what is the circuit we have created. And just like the previous example, the iteration in the previous 10 iterations was taking place in the previous example. Here epochs are taking place, but number of epochs in this time, the number of epochs equal to 30. So if we run this particular code cell, we are getting this particular circuit, that is 2 qubits we have taken, and we have applied Rx gate on both the qubits, Ry gates in both the qubits, and between two one entanglement layer, and another Z gate we have applied. Just sometimes back I have explained that Rx gate, Ry gate, one entangling layer, and another expressive RZ gate. So we have defined 30 epochs. So for epochs, it is showing that the loss is epoch 0. At epoch 0, the loss is 0.1035. The weights are initialized with 0. Weights are initialized 0.1, 0.2, 0.3. So weights are varying. That is, now new weights are, by applying quantum gradient descent, the new weights are 2.5333, 0.2, 0.3. So for this particular, in the same way, for epoch 5, epoch 10, the loss is this, the weights are updated to. And for this particular example, what we can see from here, that the first weight, that is W1. W1 is the most expressive and most decision making weight for this particular toy example. This one, that is why this particular weight is changing its values. This is the most decisive factor. And the predicted probabilities measure all. We have used the function measure all, means these two qubits are there, all the qubits are measured with the measurement. Once it gets measured, we are getting the classical values. So it is predicting the class equal to 1, the probability of the sample of belonging to class 1 is equal to 0.25%. 0.25% means the level is 0. Similarly, the probability of belonging to class 1, this is equal to 1%, means definitely it is a class 0 sample. Similarly, this is the probability, that is 97% probability of being from class 1, of being the sample from class 1, and this is the 99% probability of being the sample from class 1. So this particular in this particular prediction, the toy example has correctly identified all the 4 samples. So what we can say from here, that with very less number of parameters, how many parameters are there? Only 1, 2, 3, 4, 5 parameters are there. But we have taken one example of VGG16, almost what we have, almost 138 million parameters are there. So what is the advantage of using quantum neural network, that I have discussed in one of my previous slides? Means what is the motivation actually? Why we are actually interested to develop this field? And this field is very much promising. Why actually? Because the motivation is that it requires limited number of samples, it requires limited number of learnable parameters, it saves the energy, it saves computational effort, it saves memory space, it is computationally efficient, it is time complexity is less. So for quantum neural network training, with quantum neural network training, we are heading towards, or at least we are hoping to head towards, the bright future of quantum machine learning. So with this, I am concluding my today's session, and I'll be happy if some queries are there. I'll be happy to answer these queries. Thank you, everybody.
Thank you, Mahua madam.
I
There
think,
are some question in the please
okay.
continue.
Okay.
There are some question in the chat box. So, Ma'am Orpita De has asked that can QML be run on Google Colab or AWS or on general GPU? That is the first question.
Actually, I have shown that I have run all the codes in Google Colab that I have shared. Google Colab I have shared. So you can run the program in Google Colab using Penny or using Qiskit or some other languages, using the simulator. Or if you want to use the quantum hardware, in that case you have to take the service from the quantum service provider. So many quantum service providers are there. So you can take the service from IBM Cloud, or you can take the service from AWS Cloud. So many service providers are there, which actually provides you the platform as a service, PaaS. Actually, the platform as a service means I have shown you one example of AWS cloud platform execution. That particular system was executed in IonQ Area 1 QPU quantum processing unit that is located in North America, but we have used it through quantum AWS service provider. So I think the question has been answered properly.
But participant, if you have any question, you can directly ask to ma'am. You can unmute yourself and directly ask to ma'am. So I think there are no more questions. Partho sir, can you please conclude this session?
Yes, sir.
Thank you.
Thank
Thank you, everybody.
Thank you, Moali.
thank you, madam,
Madam,
for
I
a
have
nice
one
presentation.
question.
And
Yes, yes,
Madam,
okay, sure.
I have
Yes.
one question.
yes.
Actually, when you were discussing about the security issue of the data, medical data, if we apply the machine learning algorithm and if we apply machine learning, what will be the difference in security issue? Because when we are
No,
getting
actually, I was discussing about security issues because we have developed federated model. That is why, because we have developed a distributed model. That is why, if you run your model locally in your machine using whether you are using classical neural network or you are using the quantum neural network, there is no problem of security. I have discussed about the security of raw medical data because I have implemented the distributed learning model. That is why. That is, the
Okay.
model is distributed over the network.
Okay,
And
okay.
different medical service providers, say I have given one example in my lecture also. Say one service provider is situated in India, another service provider is situated in North America, and they are collecting their patient samples. We are collecting our patient samples, and all those samples are learned over there in the local model. And after that, those model parameters are shared to the cloud. That is why security issues come into the scene.
Understand.
So,
So
thank you,
if,
madam, for a nice presentation and vivid explanation in a very lucid way. Also, the demonstration was very nice. I hope there are no more questions. With this, I want to close this session. Please wait for the next session.
Okay. Thank you everybody. I think Dept madam is present. Please take.
Yes, ma'am, I'm here.
Okay.
Am I audible?
Yes, you are audible, madam.
Okay.
Ma'am, with your request, with your permission, can I pause or stop the meeting recording for 1 or 2 minutes?
Yeah, sure.
Yeah, thank you.